Hello, everyone. We are back with yet another class today. So, hello, everyone. So, the topic for today is going to be searching, right? So, we are going to look at different searching algorithms. We will start with linear search, and then we will move on to binary search. We will look at ternary search, and we will solve some problems related to binary search. Okay. Now, as always, after the class, we will have an assignment for you guys. So, after every class, you are given an assignment so that you can actually apply what you have learned in the class and solve problems so that you can solidify the concepts. The link for the problem set will be in the video description. Apart from that, there will also be a link for a chat forum so that you can talk to your peers and discuss any issues that you face while solving problems. So that is for today. There is one more announcement that I would like to make, which is that a lot of students come to us and they say that, hey, I need help with interviewing, right? So they tell us that they somehow get nervous during interviews. And a lot of students say that when I'm doing competitive coding online, I am able to solve problems. But when I'm in a face-to-face interview, I somehow get nervous or I'm not sure what the correct approach or what correct approach should I take while solving the problem in an interview. So to handle that, we have organized a mock interview for you guys today, right? So suppose that you wanted to see how an ICPC World finalist, right, someone who is very strong at data structures and algorithms, how such a person would behave, would approach a problem in a Google interview, right? So today at 8 p.m., we are going to have exactly that. We have our candidate, which is an ICPC World finalist, and we have an interviewer who is an ex-Googler, and they will be doing a mock interview for us. All right. So stay tuned for that. That will be at 8 p.m. today on Scalar YouTube itself. All right. Without further ado, let us dive into today's lecture. So let me just share my screen. All right. I hope that this is visible to everyone. Can someone just confirm, please? Perfect. All right, let's begin. So I assume that most of you would be familiar with some sort of searching, right? Suppose that you have a collection. Suppose that you have a haystack. And you are looking for something in this haystack, right? Suppose a needle. Then how do you usually search? Well, the way we usually search is we pick each item one by one. Pick each item one by one. One by one. And we inspect it. Right? We see if this is the correct item, if this is the item that we are looking for. Now, this can be very, very time consuming, right? So just to prove this point, let us play a very simple game. Okay? So I want you all to play this game. So I have a number in my mind, right? And I'm telling you that the number is between 0 to 1000. Okay. Now, what you're supposed to do is you're supposed to guess what the number in my mind is. I'm not telling you the number right away. So you're supposed to make guesses between 0 and 1000. So if you could please start spamming in the chat, just tell me your guesses in the chat. And whenever I see the number that I'm guessing, that is in my mind, I'll let you guys know. All right, so can you guys please start? So I have a number between 0 to 1000 in my mind, and you have to guess that number. So start placing in the chat. What do you think the number is? You have no other information. 786, not really. That is not what I had in my mind. Okay, I got 52, 30, 91, 900, 100, 99. No, none of those. A lot of zeros, some 500, some 304, 300, 666, 120, 76, 2. None of these. 50, no, 3, 404, 545. None of these. None of these. Please give some hint. So Tushar has a very important thing over here. Tushar says, if you could give us some hint, then we will be able to approach that particular solution much faster, perhaps. Right? So we see that if you have no information, Right? If you have no information about how to search, then your best chance is to randomly check, randomly guess, right? Or if you don't want to randomly guess, your best chance is to basically check each possibility, right? So it could happen that first you say that, okay, you are guessing the number 1, then you move on to number 2, then you move on to number 3, and you keep doing that, you keep making guesses till I say that, yes, your guess is correct, right? So this is an example of something called linear search. Why linear? Why linear? Because you are going over each item linearly, right? Basically, you're going over each item once. So this is called linear search. And let us suppose that you have n elements, and you're looking for some value. Right? You're looking for some key in this set of n elements. Then how much time will linear search take us? So what is the time complexity of linear search? It is order of n time, right? And while we are at it, let us also quickly discuss the space complexity. So how much space does it take to do a linear search? Well, this is just order of 1, right? Because we don't really have to store a lot of memory. We can just use a couple of temporary variables and perform the linear search. All right. So I assume that everyone is familiar with this linear search. So linear search is very inefficient. Now the question comes, can we search faster? Can we search faster? Right? What do you think the answer to this is? So this is the question. Now I'm asking you, what do you think the answer will be? Now, as most things in life, the answer is it depends, right? It depends. Well, it depends on what? It depends on, is there some pattern in the data that we can exploit, right? If we have some pattern in the data that we can exploit, then perhaps we could search faster. Does that make sense? For example, let us play this game once again. Right? Let us play this game once again. I am going to have a number from 0 to 1000 in my mind, and you are supposed to guess that number once again. However, this time, whenever you make a guess, I'm going to tell you if your guess is too high or if your guess is too low. All right? Cool. So let us begin once again. I have a number in my mind, and could you start guessing, please? So Mudasir says 2. Well, 2 is too low. Then Mudasir has guessed 34. 34 is too low, once again. Then the next guess is 123. It is too low. The next guess is 233. That is too high. Sahil says 500. That is too high. All right. Keep them coming. Keep the guesses coming. The next guess is 150. This is too high. Then, what is your next guess going to be? So 188. No, 188 is still too high. 200 is still too high. 10 is way too low. Yes. So 130. 130 is too low. And then what do we have? All right. So 130 is too low. Can you make more guesses now? 143, right? Someone guessed 143, and that is exactly the value that I was thinking of, right? This was my guess. This is correct. All right. So we see it took us some time, right? It took us some time. It was not that we were able to guess the answer immediately. However, we were able to hone in on the answer, right? So you know of homing missiles, right? The homing missile doesn't really know where the target is, but as it moves forward, it will get closer and closer to the target. Right? That is what we were able to. We were able to home in, right? Home in on the answer. Why were we able to do that? Because there was some pattern in the data that we could exploit. The pattern was that we were able to figure out whether our guess was too low or whether our guess was too high. Right? Now, a lot of students think they have this misconception that some sort of a binary search, right? Binary search can only be applied when the data is sorted. And that is not the case. The data need not be perfectly sorted for you to be able to apply binary search. Right? So what we are looking for in the data is we are looking for some pattern or some sort of ordering. Okay? So let us define some nomenclature over here. Let us define some theoretical nomenclature over here so that we can make concrete progress over what binary search is. All right? So suppose that you have some search space. And let us represent the search space like this. In the search space, this search space is basically a set of possibilities, of possible answers. Right? So there's one answer possible over here. So this is another possible answer, this is another possible answer perhaps, another possible answer, and so on. Excuse me. So what binary search says is that when you make a guess, let us suppose that you made this as the guess. When you make a guess, if you are able to eliminate, a large fraction of your search space, then you can search efficiently. If this is the case, then you can search efficiently. Right? Let's see how. So let us look at the previous game that we played. In the previous game, whenever you came up with an answer, right? Let us say that you came up with an answer that, hey, the guess is 200. Then all I told you was whether the guess was correct or not. Right? All I told you was whether the guess was correct or not. And that basically allowed you to eliminate this possibility itself. Right? So you made a guess 200. I told you it is not correct. So you can eliminate this possibility. Can you eliminate any other number? Did you get information about any other number? You did not. Right? On the other hand, in the second version of the game, suppose you guessed 200 and I told you that it was too high, then you could have eliminated every number. You could have eliminated all these numbers that were greater than 200. And your search space would only remain with the numbers that are less than 200. Right? Does that make sense? Yes? So, oh no, don't worry guys, I don't have corona. I'm just suffering from cold. So, this is something that we will try to exploit in binary search. So basically, binary search can be applied whenever you can remove, right? Remove or prune a large chunk of your data, of your search space with every guess. All right? Cool. So let us look at a more concrete example of this. So mostly when we are talking about searches, the first thing that would come to our mind is that we have an array. Right? We have an array. Suppose we have an array of integers. Right? This array has multiple values. Let us say that the size of this array of size n. The size of this array is n. And we are supposed to search for a particular value in there. So given an array, what type of things are we able to binary search over? So whenever we try to binary search, we try to come up with a proposition. Does everyone understand what a proposition is? Yes? A proposition is something that takes two values, any of two values, right? A proposition can either be true or it can be false. Right? A proposition can either be true or it can be false. Now, if you can come up with a proposition, such that your array starts looking something like this, that for this particular element, the proposition is true. For this element, the proposition is true. For this element, the proposition is true, and so on. At some point, the proposition starts becoming false, right? If you are able to come up with a proposition that can make your array look like this, then you are able to perform binary search on this array. And what will that binary search give you? That binary search will give you this boundary point. That binary search will give you this point where the proposition flips. All right, is that clear? So we will look at a little more concrete examples of these. We will look at a little more concrete examples of these. Cool. So let us once again go back to this game of guessing the number. Right? Let us suppose that I gave you an array from 0, 1, 2, all the way till 1000. Right? All the way till 1000. And I had a guess. Let us say my guess was this number G. The correct answer was this number G. Now, what is my proposition over here? What is my proposition over here? So what is the proposition that makes sure that everything to the left of G is true and everything to the right of G is false? Can someone tell me that? So what proposition should I make so that every number to the left of G should result in false, while every number to the right of G should return in true? Exactly. So the proposition can be as simple as, is A of I less than G? Right? Is A of I less than equal to G? Right? What happens in that case? So if G is my guess, over here, then every value to the left of it, yes, it is less than equal to G. So all these values will be true. All these values will be true. On the other hand, on the right hand side, all these values will be false because they will be, if the array is sorted, all these values will be false because they will be larger than G. So if I'm able to come up with this proposition, then binary search will allow me to find this junction. It will allow me to find this point where the true flips from true to false. Is that clear? All right. And now we have basically come up with the final definition of binary search. Right? Binary search does not require you to have a sorted array. Right? That is a misconception, that you need to have a sorted array to perform binary search. What you really need is you need this proposition. If for any search space you can come up with such a proposition, then you can apply binary search on that search space, right? Irrespective of whether that search space is sorted or not. All right. Perfect. So let us dive into some more concrete things, and let us try to look at the implementation of binary search. Right. So once again, suppose that we have been given an array, right, of size n, and this array is of integers. Right? And we are also given a key, suppose k, that we are looking for. And for now, let us suppose that the array is sorted in ascending order. Right? Then what we have to do is we have to search the element. We have to find the index of k in this array, if it exists. Right? If it exists in the array, then we are supposed to find the index and return the index. Otherwise, what we are supposed to do is we are supposed to return the index where k should be inserted. K should be inserted in the array. Is that clear? Yes, is that clear? So once again, suppose that we have an array that looks like this: 0, 3, 7, 12, 15, 16, 20, right? And I give you the key, let us suppose 12, right? So in this case, what are you supposed to return? So let me give the index as well. This is 0, 1, 2, 3, 4, 5, 6. So in this case, what are we supposed to return? If this is the array and this is the key, then what value will we return over here? The answer we are supposed to return over here is the index 3, right? Because 12 is at the index 3, right? On the other hand, if I ask you to find the value, let us say k equals to 17, right? If I ask you to find the value k equals to 17, then what are you supposed to return? So there are multiple variants, right? In some cases, I might ask you to return -1 because 17 is not present in this array. I might ask you to return -1, but that is not what we are looking for over here. We are saying that if the value is not present in the array, then tell me the index where that value should be inserted. Right? So if 17 was inserted in this array, then what value, what index should it be inserted at? Should it be inserted at this location? Should it be inserted at this location? No, it should not be, right? Because 16 is less than 17. It should be inserted at 20's position, and 20 should be shifted to the right. Yes, 17. If 17 was inserted, 17 would come in the 6th position, and 20 will be moved to the right. Right? So if the search key is 17, then you are supposed to give me back the answer index equals to 6. Is that clear? Right? So this is the classic problem of binary search. We have been given an array. We have been given an array which is sorted, and we have been given a key, and we have to search this key within the array. Right? Now let us first look at the implementation of how we would do this binary search, and then we will discuss the time complexity, right, and the corresponding analysis. All right. So let us start with this thing. So suppose that we have this function int binary search, right? And in this we are receiving a vector, right? We are receiving a vector. So we can say that, okay, we have an vector AR, vector of int AR, right? Apart from that, we also have the key. So we have an int. So this is not a semicolon, this is a comma. We have an int key. All right. This is the function that we are going to write. Yes, Shubrata, yes, in this case, we are accepting a sorted array. All right. We will come to binary searching over non-sorted arrays in some time. We are starting with the most simple thing, that the array is sorted. All right. Cool. So how would we write this particular piece of code? So when binary searching, there are certain things that we would like to identify. There are certain things that we would like to identify. If we are going to search, then the first thing that we need to identify is our search space, right? Is our search space. Now, if we have an array, then what do you think the search space is going to be? If we have an array, then what is the search space? Well, the search space is all the possible different indexes in the array, right? The value could be at index 0, the value could be at index 1, and so on till the last index. So the search space is the indices of the array. Well, what is the minimum value of that search space and what is the maximum value of that search space? So can we somehow draw a boundary? Can we draw a boundary around the search space? Yes, right? So in this case, the boundary is from 0 all the way till n minus 1, where n is the length of my array. Is that clear? All right. So when I'm defining the boundary, I will encapsulate. I will basically wrap my search space around this within this boundary. So I will say that, okay, let us suppose that we have some low, right, and that is the minimum possible value in my search space. Excuse me. Excuse me. And I also have some high, and that is the maximum possible value in my search space. Excuse me once again. And I can write over here that n is perhaps n equals to ar.size. All right. Cool. Now that we have the boundary, we are supposed to perform the binary search. Okay. So this was the first step of binary search. The first step of binary search was to bound or to establish the boundary of the search space, right? The second thing Once you have established the boundary, the second thing is to make a guess. To make a guess. So how do we make a guess? Let us suppose that we have some search space and we want to make a guess. What guess do you think we should make? What guess do you think we should make? So we can make any guess, right? We can make any guess. However, we should try to make a guess that allows us to eliminate a very, very large chunk of the search space, right? Does that make sense? So if I have this array, and this is sorted, right? And this is my low, and this is my high, right? If I make this guess, if I make a guess over here, then what will I be able to eliminate? What will I be able to eliminate? I will either be able to eliminate this part or I will be able to eliminate this part. Yes, I will either be able to eliminate this left half if my guess was too high, right? Or I will be able to eliminate this right half entirely if my guess was too low. Now, what is these values? What are these values over here? What are these values over here? Let us say that this is x, then this will be n minus x, right? Now the question is, in the worst case, right? If I'm very, very unlucky, then my guess will be on this side, right? I will be able to eliminate a smaller value. I will not be lucky. I will not be able to eliminate a very large value, right? So I should try to make it so that x is as large as possible, right? Both x and n minus x are as large as possible, right? So that no matter whether I'm lucky or not, I'm able to eliminate a large chunk of my search space, right? So what guess should we make over here? We should perhaps guess the middle element. We should perhaps be guessing the middle element. Is that clear? Right? So this is the second thing. Once we have decided the search space, once we have the low and the high, now we are supposed to find a mid. Right? So we will guess a mid. So we will say int mid equals to low plus high by 2. Right? And notice that this is integer division. Right? This is integer division. All right, cool. So is this part clear? Is this part clear? That we calculate the mid. All right. Once we have the mid, then what do we do? Once we have the mid, then what do we do? The third step is to check the proposition. Check the proposition. And prune, right? And prune our search space. Right? We have to check the proposition and prune our search space. Now, the proposition can be either true or false. Right? The proposition can be either true or false. However, in most of the cases, we can have 3 values. Right? We can have 3 values. Either my guess is too high, or my guess is too low, or my guess is exactly correct. Right? So let us look in this case. Let us look at that in this case. So what possibilities can I have over here? Right? What possibilities can I have over here? If AR of mid is less than the value I'm looking for, is less than the key. Right? If AR of mid is less than the key, then what does that mean? Is my guess too high or is my guess too low? If the location that I'm looking at the location mid. If the element at that location was less than the key, then is my guess too high or is my guess too low? Well, the element was less than the element I was looking for. So I am sure that since the array is sorted, any value that is at AR of, let's say, 0 or AR of mid minus 1, right? Mid minus 1, all these different values are going to be less than the key as well, because the array is sorted. So my guess was too low. Right? My guess was too low. So what should we do? We should adjust something, right? We should adjust the search space. How should we adjust the search space? We can say that low equals to mid plus 1. Right? Mid plus 1. Right? So basically, earlier This was the search space, this was low, and this was high. Right? I made the guess at mid. And I found out that this guess was too low. Right? This guess was too low. So what should I do? I should shift this low. I should shift this low to the element just right of it. Right? So this element should now be low. And basically by doing that, I am eliminating all these different possibilities. Right? I am eliminating all these different possibilities. Is that clear? So we should move up the low. Is that clear? We should increase the low. All right, so that is one case. So what other cases can we have? Else if AR of mid was greater than key, right? If AR of mid was greater than the value I am looking for, then what happens? Then my guess is too high. And by the same argument, now I need to decrease the high. Right? And now I need to say high equals to mid minus 1. Right? Otherwise, if even that is not the case, then what possibility remains? If it is neither too high, if it is neither too high nor too low, then what possibility remains? Then it must be exactly correct. Right? Else my guess was exactly right. Right? I guessed the perfect answer. So in that case, I can just return the index. Right? Because I looked at this particular index, AR of mid, I looked at this particular index and I found a value that was exactly equal to the key. Right? It was neither greater than key, it was not less than key, so it must be exactly equal to the key. So I can just return this index because this is the index that I am looking for. Is that clear? Yes? Perfect. Now let us look at the code that we have and let us see if there is something missing over here. Right? Let us see if there is something missing over here. So once again, in the code, what we are doing is we are saying, let us initialize a search space. Initialize space, right? Then we make a guess. So this is our guess. And based on the guess, we adjust the search space. So will we be able to, after one adjustment, will we be able to reach the answer? Will we be able to reach the answer after just one adjustment? No. Right? We have to continuously adjust our guess. Right? So we have to do this entire thing again and again. We have to repeat this. Right? We have to repeat this entire thing. So how should we repeat this entire thing? Let us put it inside a loop. So let me add some space over here. And let me say, I will loop. Let us say I loop forever, right? While some condition. So I don't really know what this condition is, but as long as this condition is true, I will keep looping. Right? I will keep looping till this condition is true. Is that clear? Right? So we could have done several things over here. We could have called this function recursively as well. Right? Based on the adjusted guess, we could have called this function recursively as well. But recursion will have a lot of different issues with itself. So it will use a lot of memory because it will use the recursion stack. So let us not do that. Let us go with the iterative approach. Right? So once we have made a guess, and we check the guess, after we check the guess, we will adjust our search space. Right? Now once we have adjusted the search space, what do we have to do again? We have to make the guess again. Right? We have to make the guess again and again. But till what time should we continue this? Till what time should we continue this? Should we continue this forever and ever? Should we continue this forever and ever? No, we should only continue this as long as our search space has elements in it. Right? If our search space has elements in it. So basically, if our search space is empty, then it does not make sense to keep looking inside that search space. Right? If our search space is empty already, then it does not make sense to keep looking inside that search space. So when will our search space be empty? Right? When will our search space be empty? Let us suppose that this is my array. This is the low and this is the high. At what point would I say, for what values of low and high would I say that my search space, that this particular area, this particular range over here, this is empty? When will I say that? What happens when low equals to high? When low and high are the same. What happens when low and high are the same? Well, then my search space is not empty. Then my search space has one element, which is a of low. Right? If low equals to high, then my search space has one element, which is a of low. So when will my search space be empty? When low will be greater than high. Yes. As soon as this happens, as soon as this is my low and this is my high, right? Then I'm saying that the search space is everything that starts from low and goes till high. Well, it cannot go till high, right? My search space is empty now. Is that clear? So I am supposed to continue this loop till my search space is not empty, right? So what will be the opposite condition over here? What will be the opposite condition over here? So if this tells me that the search space is empty, then how do I check if the search space is not empty? I will check it by saying while low is less than or equal to high. Is that clear? Yes? Right? And this is very important. Right? If you miss this equal to, you might get an incorrect answer. Right? Or if you do something else, you might run into an infinite loop. So it is very crucial that we have this condition right, because this condition tells us when to terminate. It tells us when our search space is empty. Okay? And I mean, a lot of the times people are worried that, okay, I don't really know how to determine what condition should go over here. So here's the trick once again. To determine what condition should go over here, you have to ask yourself, when will my search space be empty? When will my space be empty? Right? And based on that, you will be able to come up with a condition. All right? Cool. So this is basically the code of binary search. We started with a search space. Repeatedly, while the search space was not empty, we made a guess and we adjusted that guess. Right? If our guess was perfect, we simply returned that guess. But what if we did not find that element? What will happen then? What if we did not find that element at all? What will happen then? Well, then we will keep on looping. Till the point our search space becomes empty. Right? Till the point our search space becomes empty. So what will happen is we will not be able to return over here. However, we will come out of this while loop. Right? So we will come out of this while loop. We will be over here at this point. And what values of low and high will we have? We will have a value such that low will be equal to high plus 1. Right? That is when our search ends. Right? And what is this location? Can you tell me what this location is? This location is exactly the location where I should insert this element. If I were to insert this element, this is exactly the location where I should insert this element. So when I am at this point, just give me a second. When I am at this point, I know two things. The first thing I know is that low is the index. Is the index where I should insert it. Where I should insert key. If I was going to insert it, then low is the location where I should insert it. Second thing I know is key was not found in my array. Key was not present in my array. Right? Is that clear? Now, once again, if we were to simply find the index of the, if we were supposed to find the index of the key and return -1, if the key was not present, then over here we will return -1. Right? Then over here we will return -1. Right? On the other hand, more practically, whenever you see a library implementation, we don't usually return -1. Instead, we return the index where I should have inserted the key. Right? So over here we can also return the low. Return the low value, right? Because this is the location where I should have inserted the key. Is that clear, guys? Yes. Now, one common question is, if you are returning -1, then your caller knows. That the element was not present, right? Because hey, index cannot be -1. Index of a particular value in an array cannot be -1. Indexes start from 0, right? So in this case, my caller knows that the element was not present. But what if I return low? What if I, instead of returning -1, what if I return low? How will the caller find out if the element was present or not? Yes, the caller has to be able to make that distinction, whether the element was present or not. So how will the caller get to do that? Well, the caller can check. The caller can simply check. So it will say that, okay, index equals to binary search, the array and the key, right? And the person can check, the caller can check if AR of index equals to key, right? If AR of index equals to key, then we found the key, right? Then we found key at index, right? Otherwise, it means that we did not find the key, but this index is the location at which we are going to insert it. If we were to insert it, so we can say did not find the key, but if we were to insert it, it should be inserted at index. Is that clear? So the caller will have to make this additional check. Is that clear, guys? Yes? Okay. So Rohit has a question over here. Rohit says, what should we return? What should we return if key is less than AR of 0? Right? That's a very good question. So suppose that we have this array. This is the index 0, this is the index 1, and so on. Right? Let us say this value is 10, this value is 11, this value is 12. And let us say my key was 9. Right? Or let us say my key was 5. So first of all, is my key in the array? Is my key in the array? No, it is not in the array, right? Not present. Not present. If I were to insert this value, where should this key go? If I were to insert this value in the array, where should this key go? Can the key go at location -1? No, right? There is no index -1 in the array. So where should this key go? This key should go at index 0. The 5 should be inserted over here, and everything in the array should be shifted to the right. Right? Shifted 1 to the right. Does that make sense? So over here, our binary search, when I search for key equals to 5, my binary search should return the value 0, right? It should return the index 0. And that is exactly what our code will do. All right, that is exactly what our code will do. Is that clear? Okay. So let us move on. So I hope that the code and the implementation of binary search is clear to everyone. Now let us look at some improvements that we can make on our code. So one of the most important improvements is that we never try to calculate. We never try to calculate the mid like this, right? And you might have seen this a lot of times. People do the following. People instead of saying int mid equals to low plus high by 2, right? They do something else. They say int mid equals to low plus high minus low plus high minus low by 2, right? So can someone tell me the difference between these two? Can someone tell me the difference between these two? Why do some people do it this way? Why do some people do it this way? Well, let us try to look at the mathematics, right? Let us try to look at it mathematically. So if I have low plus high by 2, right? This is one thing. On the other hand, I can have low plus high minus low by 2. And let us see that if there is a difference between these two. So what I can do is I can take the denominator 2 common over here. So what will happen? The numerator, this will become 2l plus h minus l. Right? This will become 2l plus h minus l. What is that? That is simply so one l will cancel out. This will simply be low plus h. Right? This will simply be low plus h. So we see that the left hand side and the right hand side are equivalent. Right? From a mathematical point of view, they are equivalent. So what really gives? Why do people do this? This is more complicated, right? The reason why people do this is, even though they are mathematically equivalent, when we are dealing with computers, we can run into an overflow, right? When we are doing addition, we can run into an overflow. For example, let us suppose that our integer can only store. So let's suppose that the largest value our integer can store is, let us say, 10 to the power 9, right? Let's say 1 billion. Okay. Let us say that our low is 5 into 10 to the power 8. Okay. So our low is 500,000. Let us say that our high is 8 into 10 to the power 8, right? Which is 800,000. Right? If I have something like this, what will happen when I try to calculate the mid? What will happen when I try to calculate the mid? I will be doing 5 into 10 to the power 8 plus 8 into 10 to the power 8, right? This will be low plus high, and then I will divide it by 2. Yes, then I will divide it by 2. But what will happen over here? When I try to add these values, this will be 13 times 10 to the power 8. Right? And we just saw that 13 into 10 to the power 8, this cannot fit in my integer. My integer can only be up till 10 to the power 9. This is greater than 10 to the power 9. Right? This is what? This is 1.3 times 10 to the power 9. Right? So this value over here, this will overflow. This will overflow. And the value that I will get over here will be garbage. Right? It will give me a wrong answer. And then I divide the wrong answer by 2. I will eventually get a wrong value of mid. Is that clear? Yes. On the other hand, if I do it the other way, if I say low plus high minus low by 2, right? If I do it this way, then what happens? Then this will be 5 into 10 to the power 8 plus 8 into 10 to the power 8 minus 5 into 10 to the power 8 by 2, right? And is this operation going to overflow? No, I'm subtracting things. Right? I'm subtracting things. So the answer over here will be less. Right? The answer over here will be less than this value. Yes. So what do I get over here? I get 5 into 10 to the power 8 plus 3 into 10 to the power 8 by 2. Right? And then then this will give me the correct answer, 6.5 into 10 to the power 8. Is that clear? This will not overflow. Whereas this approach will overflow. Is that clear? This approach will overflow. All right. So Amit over here says that, hey, we can just use a different data type. Right? If we are dealing with an integer, maybe we can switch to a long data type. Right? But I mean, what if you were using a long? Right? Amit, the problem is, what if you were using a long? What would you do then? So in general, it is a good idea to implement the mid calculation via this particular approach. Okay. All right. So that is the improvement we are going to make over here very quickly. We are going to go to our code of binary search. We are going to remove this and we are going to improve it. We are going to say int mid equals to low plus high minus low by 2. All right. Perfect. Okay. I hope that everything is clear till now. Now let us try to analyze the time complexity of binary search. All right. Let us try to analyze the time complexity of binary search. Time complexity. All right. So how do we talk about the time complexity of binary search? So what is really happening is, initially I have the search space of size n. Right? Initially, I have the search space of size n, and I guess the midpoint. Right, as my guess. Right? If my guess is too low, then I'm able to remove these elements. Right? I'm able to remove these elements. How many elements was I able to remove? So if this is 0, this is mid, and this is n, then after one guess, if my guess was too low, then how many elements was I able to remove? I was able to remove n plus 1 by 2 elements. Right? Yes or no? On the other hand, if my guess was too small, then I would be able to remove all these different elements. Right? Everything from mid all the way till n minus 1. Right? Even then, I was able to remove n plus 1 by 2 elements. Right? I was able to remove n plus 1 by 2 elements. So what really happens is, every time I make a guess, I'm reducing the search space by half. Right? I'm halving the search space with every guess. every guess. Right? So suppose we started with this guess n. Right? We started the search space of s of n. After one guess, I will have a search space of n by 2. After one more guess, I will have a search space of n by 4. One more guess, I will have a search space of n by 8. Right? And when will I end? So finally, this search space will reduce down. This search space will reduce down to just one element. Right? This search space will reduce down to just one element. Is that clear? So the question is, how many guesses did it take? So it took me one guess over here, it took me one guess over here, one guess over here, one guess over here, and so on and so forth. So how many guesses did it take? Right? How many guesses did it take? No, Tushar, that is not correct. No, Prakash, that is not correct. So no, guys, it did not take me n plus n by 2 plus n by 4 all the way till 1. No, this is not how many guesses I got. Right? This is incorrect. So remember that when we are moving from this search space to this search space, I am making one guess. I am not making n guesses over here. Right? I made just one guess and I was able to reduce my search space from n to n by 2. Right? So basically, at the 0th guess, when I have not made any guess, my search space is of size n. After first guess, right? After first guess, my search space is of size n by 2 to the power 1. After second guess, my search space is of size n by 2 to the power 2. After the ith guess, my search space will be of the size n by 2 to the power I. Right? Now the question is, at what value of k? At what value of k will this thing become equal to 1? At what value of k will my search space reduce to one single element? That is the question that we are asking ourselves. So this is the equation that we get, right? So at the kth guess, our search space will be this, and we want the search space to have just one element. So can we find the value of k from here? Can we find the value of k from here? So what can we say? This implies that n equals to 2 to the power k, which implies that I can take log on both sides. Right? I can take log base 2 on both sides, log base 2 of 2 to the power k, right? Which implies that k equals to log base 2 of n. Is that clear? Yes. So I am taking order of log n guesses. I am making order of log n guesses, right? And that is the complexity. That is the time complexity of binary search. Is that clear? Yes? Is that clear, guys? So basically, we started with an array of size n. Then after first guess, we were able to reduce it to half the size. Then after the second guess, we were able to reduce it to 1/4 the size, and so on and so forth. So how many guesses will we take to reduce it to size 1? Well, it will take us log base 2 of n guesses. Right? The depth of this tree, the depth of this is log base 2 of n. Is that clear? Right? Okay. What about the space complexity? What about the space complexity? So let us go to the code to analyze the space complexity. Let us go back to our code and let us see what variables we are using. Right? So this is our code. Let us see what variables we are using. So we are declaring a variable over here, n. We are declaring a low, we are declaring a high, and we are declaring a mid. Right? All of these take constant space. They are just integers. So overall, our space is just constant. Right? We are not allocating any space that is dependent on the input. We are just allocating a constant space. Right? Notice that this vector, we are not allocating this. This is given to us already. Given to us. Since we are not changing this array at all, so we don't have to allocate the space for the array. All right? The array is given to us. So the space complexity of binary search is going to be simply order of 1. All right? Constant space. Is that clear, guys? Perfect, perfect, perfect. Now let me ask you a question. Let me ask you a fun question over here. So this is called binary search. Right? This is called binary search. Binary search. Why is it called binary search? Because we are splitting into two parts. Two parts with every guess. Right? And we saw that when we do binary search, our complexity turns out to be log base 2 of n. Right? Our complexity turns out to be log base 2 of n. What if instead of binary search, what if I try to come up with something like ternary search? What if I tried to come up with something like ternary search? So first of all, how would ternary search even work? Right? How would ternary search even work? If I have this particular array, then now I have to guess two values. I have to get mid 1 and I have to get mid 2. Right? This is my low. This is my high. In ternary search, what I can do is I can make two guesses. Right? I can make two guesses. I can say mid 1 equals to low plus high minus low by 3. Right? And I can say mid 2 equals to low plus 2 times high minus low by 3. Yes or no? Can I do that? And then I can compare. Right? Then I can compare. So I can compare AR of mid 1 with my key. Right? I can compare AR of mid 2 with my key. Right? And what will I get? What will I get? Either my key will lie in this area, or my key will lie in this area, or my key will lie in this area. Yes, that is all the possibilities, right? My key cannot lie in both these areas at the same time. Right? My key cannot lie in both these areas at the same time. Does that make sense? So after one guess, we were able to reduce our search space by 1 to 1/3. Right? From n, we could go to n by 3. Right? We could eliminate a larger chunk of our search space. Does that make sense? This is called ternary search. This is called ternary search. And in general, you can extend this idea. You can define something called a k-ary search. And in k-ary search, what you will do is you will calculate mid 1, mid 2, all the way till mid k minus 1. Right? And then we'll compare with all of them. That will allow us to, in one guess, it will allow us to go from n all the way till n by k. Right? Does that make sense? Yes, ternary means 3 divisions. Binary means 2 divisions. K-ary means k divisions. All right? Is that clear? Example of ternary search? Well, the example is very simple, right? We given an array. What I'm going to do is I'm going to make 2 guesses. Right? Instead of making one guess at any point, I'm going to make 2 guesses. And based on these 2 guesses, I'm going to decide whether I should be looking over here, or I should be looking over here, or I should be looking over here. Right? Going back to our original question, when we were supposed to guess between 0 and 1000. Right? Instead of you giving me a guess like 500, you could have given me 2 guesses at the same time. You could have given me 333 and 666. Right? And then I could have told you that, okay, it is less than 333, or it is between this, or it is above this. Does that make sense? Yes? Does that make sense? Right? So the time complexity of ternary search, it seems that the time complexity of ternary search will be order of log base 3 of n. Right? Because we are dividing by 3 every time. Similarly, the time complexity of k-ary search would be order of log base k of n. Yes? Now, which is greater? Which do you think is greater? Is log base 2 of n more, or is log base 3 of n more, or is log base k of n more? Right? For some large value of k, which value is more? Which value is smaller? Right? So which value is larger? Which value is smaller? Well, if we divide by 2, then it takes us certain number of steps to reach 1. If we divide by 3, then it will take us lesser steps to reach 1. Right? If we divide by 3, then it will take us lesser steps to reach 1. So log base 2 is greater than log base 3n, which is greater than log base kn. Right? So it seems like k-ary search should be the fastest. Should be The fastest, right? So why do people still use binary search? Why do people still use binary search? Why don't we always have k-ary search? K-ary search seems to be very fast, right? And it seems that I can make it as fast as I want, right? I can just increase the value of k to make it as fast as I want. Yes or no? Yes? Well, let us see what is the fastest value I can have. So maybe when k equals to n, I will get log base n of n, right? Which is simply 1. So I will be able to find the answer in just one guess. That is amazing, right? I will be able to find the answer in just one guess. That's very, very weird, right? I was able to find the answer. I was able to search the element in the array in just one guess if k equals to n. Is that correct? Is that correct? Yes, but there's a catch over here. Right? Now what really happened was we had this array and we made every element as a guess. Right? We made every single element as a guess. And then we check if our guess is between over here or 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 over here, right? In one guess itself, we made we chose n different values and different midpoints, right? N minus 1 different midpoints. So are we really doing an efficient search over here? Are we really doing an efficient search over here? No, this has reduced to the linear search. Right? This has reduced to linear search. So it turns out that when k equals to n, we were expecting it to take just one guess. It did take just one guess, but inside that single guess, we were doing a linear search. Right? So this is the worst thing that we can do. Does that make sense? K equals to n is the worst thing that we can do. So what really gives? We see that our intuition does not equal our math over here. Right? Math says that this should be faster, but intuition says that this should be slower. So what really gives over here? Right? What really gives over here? Well, there's a catch. Right? There's a catch in the fact that this is big O complexity. Right? There's a hidden constant factor. Let us look at the exact complexity of searching. Right? Let us look at the exact complexity of k-ary search. If I'm doing binary search, then I have one guess, right? I have one midpoint. Yes? I have one midpoint. Do you agree? And what check am I making? I'm comparing A of mid with k. Right? How many comparisons is this? This is one comparison. Right? So my actual complexity is 1 times log base 2 of n. Right? This is in the case of binary search. On the other hand, when I have ternary search, I will guess 2 midpoints. Right? I will be guessing 2 midpoints. And then what comparisons do I have to make? I have to compare A of mid 1 with k. I have to compare A of mid 2 with k. Do you agree? Yes, I have to compare A of mid 1 with k, and I have to compare A of mid 2 with k. So how many comparisons is that? This is in fact 2 comparisons. Right? Now you see the hidden cost. As we increase the value of k, the number of comparisons for each guess increase. Does that make sense? Yes, guys. So for ternary search, our complexity is 2 times log base 3 of n. Right? This is for ternary search. And in general, for k-ary search, our complexity will be log base k of n. But for every guess, we will have to make k minus 1 comparisons. Right? We'll have to make k minus 1 comparisons. Now let us ask this question again. What do you think is larger? Right? What do you think is larger? Is log base 2 of n times 1 larger? Or is 2 times log base 3 of n larger? Or is k minus 1 times log base k of n larger? Right? Which one of these is larger? Well, now we know that actually this is the reverse, the other way around. This is the slowest This is the largest value, so this is the slowest. And in fact, binary search is the fastest. Is that clear? So we can totally do k-ary search. We can totally do a ternary search. We can totally do a k-ary search. But practically, binary search will work much, much faster. Is that clear, guys? Is that clear? Binary search will work much, much faster. Right? Cool. Now, there's this question. Now you might be thinking that, okay, you told us about ternary search, you told us about k-ary search, and then you said that, okay, those don't really matter, right? Why did you even tell us in the first place? Right? Why did you tell this to us in the first place? The reason is that in certain situations, k-ary search can become faster. Right? K-ary search can become faster. Let us look at how. Right? Let us look at how. Suppose that we are dealing with some sort of a disk, right? Hard disk. Right? Suppose that we are dealing with some sort of a hard disk. Do you know that hard disk is split into blocks and sectors and tracks? Yes. So basically, we are talking about a spinning hard disk over here. Right? We're not talking about that the new SSDs over here. We're talking about that spinning hard disk over here, the magnetic hard disk. So what really happens is, in a magnetic hard disk, you have several platters. Right? You have several platters, and for each platter, you have a read head. Right? You have a read head that is at a particular platter that is tracking a particular track. Right? That is tracking a particular track on this platter. Right? Now, what you have to do is this one track information across this one track is let's say called a track. Right? And let us say this is one block. So usually this can be something like 32 kilobytes. This could be 32 kilobytes. All right. Now what happens is, if you have to read any value within this, then that is very fast. Right? Then that is very fast because your disk is spinning. Right? Your magnetic disk is spinning at 1000 RPM. Right? So within 0.001 second, you can read this entire 32 kilobyte. You can read this entire 32 kilobyte block. Right? But if you have to change blocks, if you have to move from this sector, if you have to move from this track to perhaps this outer track, right? If you have to do that, then what you have to do is you have to move this head. You have to move this read head. So you have to unplug this read head. You have to run the motor to move it back. Then you have to plug it back, right? And that takes some time. So that moving the read head can take a lot of time. It can take, say, let us say 0.1 seconds of time. Right? So that is very, very slow. Is that clear? So it turns out that what really happens, is, it could be the case that due to this thing, it could be the case that making comparisons is fast. All right? You read 32 kilobytes of data in the memory, and then once the data is in your RAM, you are making comparisons in the RAM, right? And RAM is very, very fast, very, very fast. On the other hand, making a guess is slow. Making a guess is slow, right? Why? Because for every guess, for making a new guess, you have to change the block. You have to change the hard disk block, right? And you have to move that read head manually, right? Because this is happening in the hard disk level. This is not happening at the RAM level. Okay. So what really happens in this case is, making a guess. I want to reduce the guesses. I want to reduce the number of guesses I make. I don't really care about the number of comparisons I make, because the comparisons are happening in the RAM very, very fast, right? So in this sort of scenario, I would prefer to use some sort of a k-ary search, right? I would prefer to use some sort of a k-ary search, because in a k-ary search, this is the number of comparisons, right? And this is the number of guesses. The larger the value of k is, the lesser my guesses will be. Right? The larger the value of k is, the lesser my guesses will be. So basically, to maximize my efficiency, I choose a k which is equal to the block size. Right? And this thing, right? This thing is used all the time in databases. Whenever you are using a database, the database internally is storing the data in a thing called a B plus tree, right? In something called a B plus tree, and a B plus tree is simply a binary tree that has been extended from. So binary tree works in a binary search manner, right? On a binary tree, you can have a binary search tree and you can binary search on it. On a B plus tree, you can do a k-ary search. You can do a k-ary search on a B plus tree. All right. How did you come up with this formula? So this formula is what we just saw, right? This formula is what we saw for binary. For binary search, we have one comparison and log base 2n guesses. For ternary search, we have two comparisons and log base 3n guesses. For k-ary search, we have k minus 1 comparisons and log base kn guesses. All right. Is that clear? This is multiplication. Is that clear, guys? All right. So I think we are going to leave it at this, right? We are already above the time. So today we basically discussed binary search. Binary search. We saw how to implement it, right? We saw how to implement it, and we saw that this idea can be extended into a k-ary search, into a ternary search or a generic k-ary search. K-ary search is generally slower, right? Generally, we would like to do binary search, but there are cases, like for example, databases in which k-ary search is very, very valuable. Okay, cool. Now, I would want each of you to, once this lecture is over, to find the link in the video description, or there's a link to the assignment, right? Today's assignment. So please go over there and try to solve those problems. So those problems will be on basic binary search. There are some things that we were not able to discuss, like binary search on a rotated array, right? Finding the peak element. We can discuss it in the next class. All right. All right, guys. Cool. Will we cover interview bit problems from your website? Yes, Reshma. So all these problems. So that is why we give you the assignments, right? We are discussing the problems that are part of those assignments. Okay. I mean, of course, when we are actually doing a scalar class, when someone joins our academy, we usually have 3-hour classes, right? And we have classes every single day for 3 hours. So that gives us a lot of time to work with the student, right? So they are able to solve many more problems. We won't be able to do that on YouTube, right? So I understand that you won't be able to get the exact same experience as scalar, but that's to be expected, right? Because this is on YouTube. All right then. So please make sure that you solve the assignment. Please make sure that you are taking notes while you're studying the lecture. And see you in next class. In the next class, I will continue. We will continue with binary search, and we will be looking at more advanced problems on binary search. Okay. Perfect. If you want to join Scalar, well, we don't really announce the dates during lectures. So whenever, if you're trying to join Scalar, just go to scalar.com. Right? And any announcement about a new batch, will be made over there. Right? So please monitor the scalar.com website, and any announcement about any new upcoming batches will be made over there. Right? Okay. Cool. So let us end the lecture then. All right. Bye-bye, guys. Have a nice day. See you tomorrow, same time.